Well, that was the interlude about root systems. Now we're ready to go back to Lie algebras, and I can finally explain the classification of semisimple Lie algebras to you. So again, let G be a finite-dimensional semisimple Lie algebra. And then you have to always pick a maximal Toroidal subalgebra. I guess I'm always going to just work with the killing form, so kappa will be the killing form. And I'll just write the inner product there. That'll denote the restriction of kappa down to t, which we know is non-degenerate. And so using that, we identified t with t star. So this was all our setup back in chapter 2. And under that identification, await lambda in t star, I was just writing t sub lambda for the corresponding element of t. And we also transported the form on t to get a non-degenerate form on t star. Okay, so that was the initial setup, and then we had the Cartan decomposition. So G was T together with the direct sum of a whole load of other root spaces. G alpha is alpha arranged over the set of roots. That was the set of non-zero weights for the adjoint action of this T on G. So R here was sitting inside T star. But we did one more clever thing. We let E be the R span of R to give us a real vector space. And we showed that R sitting inside E plus the restriction of the form. So that was a complex valued form on T star, but its restriction down to E we showed was actually an inner product on E. Gave us a root system in the abstract sense that we classified in chapter 3. So I think what I'd like to do, maybe I should just prove one lemma, which we could have proved earlier. But let me prove that the Lie algebra G is actually simple rather than merely semi-simple, if and only if the root system R, constructed out of it in this way, is an indecomposable root system. Well, this is kind of straightforward, but it's kind of useful to know. So in this implication, well, let's prove the contrapositive. So let's suppose that G is not simple. So you can decompose G into several simple ideals. And then all you have to do is you let Ti be the maximal Toroidal subalgebra of T intersected with G. Then T is the direct sum of those guys, and Ti is maximal Toroidal in Gi. And then you let Ri be the roots of Gi with respect to Ti, and and that naturally embeds into R. So the whole root system is then just the disjoint union of those guys. And you let EI be the R span of RI. So that's the Euclidean space E just intersected with TI star. And then what you've got is that Ri sitting inside EI is the root system of GI, and EI is orthogonal to EJ for I not equal to J. That's by definition of Killing form. So the root system is decomposable. Okay, so that's kind of just a totally routine, just plugging away at the definitions. And once I've proved the forward implication next, actually, it'll follow that actually this decomposition of the root system in this way, coming from the decomposition of G into simple ideals, is exactly the decomposition of the root system into its indecomposable components. That just follows from the next part of the proofs. Okay, so now in the forward implication, let's take a decomposition of the root system. Maybe R is R1 disjoint union R2, with R1 and R2 being orthogonal. And if you take an alpha in R1 and a beta in R2, well, let's see, alpha plus beta alpha, well, that's just alpha alpha, which is not 0. That shows that alpha plus beta is not in R2, right? Because things in R2 are orthogonal to everything in R1. And similarly, alpha plus beta beta is beta beta, which is not 0. So that shows that alpha plus beta is not in R1. So actually, we've shown that alpha plus beta is not in R. And it follows that if you take the commutator of something in the alpha root space, something in the beta root space, well, that's in the alpha plus beta root space, but that's not a root. G alpha plus beta is just 0, so these guys commute. So now, if you consider the subalgebra of G spanned or generated by, as a Lie algebra, for alpha in R1, this fact that this commutes with all the other G betas in R2 shows that it's an ideal. But we're proving the forward implication, so we know that G is simple. So it's either 0 or G by the simplicity of G. If it's 0, you deduce that actually R1 is 0, so R2 is everything. And if it's all of G, R is R1. Either way, that proves that the root system is indecomposable. So let's do an example. I'm just going to do, I think we've talked a little bit about the SP2N before. Let me work out, let me do the even orthogonal Lie algebra in detail. Again, and I'll leave the odd orthogonal Lie algebra to you to investigate in a similar way. It's sort of a little bit more like SP2N, actually, that one. So I think I got you to do this for SP2N in homework 6. Question 4. you can do SO2n plus 1 of C similarly. And that's worth doing as an exercise too. But so I'm going to just do the even orthogonal. So let's call this thing G. So by definition, it's the subalgebra of GL2n of C consisting of all matrices. Well, I'm going to write these as block matrices A, B, C, D, so I'm doing n by n blocks. So that, let me see, let's call that matrix maybe X for short, and I want X transpose X equals 0, where this is the gram matrix of the form, and this is where I go back to this choice of form that we made long ago. So this is my symmetric non-degenerate matrix. Jn here is just, it's not the identity matrix, it's the one down the other diagonal. And if you work this equation out, right, so this is really a bunch of equations, and so if you just multiply out these matrices and equate coefficients, you see that implies that, let me see, so so this is going to be A transpose J, and then you get JND is 0. So that's from the 1-1 block when you do that. But it's better to write that equation as saying that D is minus a dagger. So I'm going to write a dagger for Jn, A, Jn. So conjugating by this matrix Jn. So this is just a natural operation. It's just flipping. Not in the main diagonal, but in that odd diagonal there. Okay, so that's this dagger map. So it's saying that the n by n matrix D is minus dagger of the n by n matrix A. Okay, and similarly, you look at the 1-2 block or the 2-1 block in this matrix equation right here, and you get relations on B and C to belong. And I think you get that, let me see, C dagger, C is minus C dagger, and B is minus B dagger. So those are all the equations that you get, just kind of plugging away at that matrix algebra in an elementary way. So that gives you the linear description of this subspace G, GL2n of C. And then what you do is you let T be the diagonal matrices in G. So and you think about that for a second, and you realize that you can have anything you like down the diagonal of the first block. But because D is minus a dagger, you've got to have minus Tn up to minus T1 in that 2-2 block. So this is an n-dimensional subalgebra. Is clearly toral because these are diagonal matrices, so they're semi-simple in the natural representation of this Lie algebra. And then I'm going to let epsilon I in T star be the map taking such a matrix H. So often I just write diag T1 Tn minus Tn to minus T1 to Ti. So just picking out the ith diagonal of this block. And one more point to make is that actually when I do this, I usually number the rows and columns of my matrices 1 through n as you would expect, but they're not n plus 1 to 2n. I then switch to minus n through minus 1. So I use that kind of funny numbering of rows and columns of matrices when I'm playing this game. Okay, so these epsilon 1 through epsilon n's, they give me a basis for T star. So now I'm going to write down some more matrices. I'm going to take I less than j less than or equal to n. I'm going to consider, let me see, eij minus e minus j minus I. And I'm going to consider ei minus j minus ej minus I. So these matrices, if you think about it, I'm using this kind of funky numbering 1 through n minus n through minus 1 for my matrices. But these guys, they basically give you the ij matrix unit up above the diagonal of the matrix A, and then it's minus dagger down in the matrix D. That was my first collection of matrices, and my second collection of matrices give me stuff in this matrix B. Remember, B is anti-symmetric in this diagonal. These guys give you the matrix units in the top left of that B matrix, together with the mirror image that you have to have down there in the bottom left, right? So I is less than j, so that's I, and then minus j. It's exactly those entries of B. So those matrices together give us kind of half of this of a basis for G. And then if you also look at, let me see, the transposes of these guys, ej minus e minus I minus j, e minus j I minus e minus I j, they give you the rest of a basis. They give you the stuff that's sort of lower triangular in A, and it gives you the stuff in C down here. So these are sort of the transposes of the ones I just took. So these all lie in G. In fact, together with T, they give a basis for G. And I was just going to note that this guy is actually an upper triangular matrix. This guy is upper triangular as a 2n by 2n matrix, and these guys are lower triangular. So what you actually deduce is that the Lie algebra G is the toral subalgebra T, together with the direct sum of the spans of all of these guys. So I'm going to just write alpha in R. And let me see, I need to take H being one of these diagonal matrices. In T, add H acts on these vectors. So in this case, it just acts as epsilon I minus epsilon j of H, and in this case, it acts as epsilon I plus epsilon j H. And here, these are minus those guys, minus epsilon I minus epsilon j of H, and minus epsilon I plus epsilon j of H. So this basis that I picked, it is actually a basis of weight vectors for this action of our toral subalgebra. So this is kind of easy to see. Remember, left multiplication on this top left block picks out the ith diagonal entry, and right multiplication picks out the jth diagonal entry. So that's that epsilon I minus epsilon j. And similarly, you get this epsilon j minus epsilon I. Here, left multiplication picks out the ith diagonal entry, and right multiplication picks out the minus jth diagonal entry. But the minus jth diagonal entry is minus the jth diagonal entry. So the commutator, actually, you get a kind of a double minus, giving that plus. You've kind of played those calculations before a little bit. So you get this decomposition of G as this toral subalgebra, and then a collection of root spaces with respect to that toral subalgebra, where the set of roots R is exactly this set plus or minus epsilon I plus or minus epsilon j for 1 less equal to I less than j less equal to n. Exactly what I wrote down. And these are all actually non-zero. So this shows, because these are all non-zero, so there's no bigger zero weight space than T. So this shows actually that T is maximal toral. And we found the root system. Okay, so then we've got to identify the bilinear form. So I'm going to use actually 1/2 of the natural trace form. So this is just the killing form scaled by some positive real scalar. It's just more convenient. And then for this, the restriction of this form down to t is non-degenerate. It's just the form there, you just multiply these diagonal matrices and take a half the trace, and then you transport it to t star, you get this induced form on t star. It just has epsilon 1 up to epsilon n being orthonormal. So that's kind of the convenient normalization of the form, so that these epsilons are an orthonormal basis. And finally, you pick a base. And the base, the standard choice of base is to take epsilon 1 minus epsilon 2 minus epsilon 3, all the way down to epsilon n minus 2 minus epsilon n minus 1. And then epsilon n minus 1 plus or minus epsilon n. So there's two guys at the end there. And it's pretty easy to see that, so that the positive roots are plus will be just these guys with a plus out front, the upper triangular ones. And every positive root will be just some positive linear combination of the guys in this base. So that is indeed a base for the root system. The positive roots, they exactly correspond to the G alphas that are upper triangular matrices, so these guys. And the negative roots are the ones that are lower triangular matrices. This is part of why this is a convenient choice of coordinates to write this down. Positive becomes upper triangular. And finally, we want to work out the so now we've got so if I let E as usual be the R span of the roots sitting inside T star, we have this root system, and we have the base. So we can work out the Cartan matrix. Hence, we can work out the Dynkin diagram. So let me do it. I'm going to just write in my base here. So it goes epsilon n minus 2 minus n minus 1. I need a bit more room. And then epsilon n minus 1 minus epsilon n minus 1 plus epsilon n. And it's very easy to work out the Cartan matrix in this case because all the roots have alpha equal to 2, and when that's the case, that's always the best normalization to pick if you can. Alpha check equals alpha, and so the Cartan entries, they're just these alpha I, alpha j's. In general, it would be alpha I, alpha j check, but the co-roots are just the same as the roots, so there's no difference. Okay, so the Cartan matrix has always got 2's down the diagonal, and then this top left part is just like a type A root system up to there. But then you find that these two guys are actually orthogonal. So this is just, my rows and columns are getting a bit confusing. But this guy and this guy has inner product -1 as well. So you get an extra -1 there. Then it zeros everywhere else. And that gives the Dynkin diagram. You have one more node. So the roots are 1, 2, 3. Then this is, so L is n here. The rank is n. So I would label that n minus 1, n minus 2, and so on. So these were the order that I picked. This was epsilon 1 minus epsilon 2, all the way down to epsilon n minus 2 minus epsilon n minus 1. This is epsilon n minus 1 minus epsilon n, and this is epsilon n minus 1 plus epsilon n. And I put in all of, so there's only one root length here. All the roots have got alpha equal to 2, so there's no double or triple bonds, no less thans or greater thans on the edges of the Dinkin diagram, and I've just put in an edge wherever there's a minus 1 in this Cartan matrix. So this is the dn Dinkin diagram. So dn is SO2n of C. And let me see, you need, well, if you really, what you want, if n is greater than or equal to 3, it's connected. So by the lemma, SO6, SO8, and so on, those are simple Lie algebras. But actually, when n is 3, it's a bit degenerate. When n is 3, it's just this guy here. That's all it is. And in fact, SO6 is just the same as A3. D4 equals A3, which is just the Lie algebra SL4 of C. So you normally start at n equals 4 when you're doing this family, so that you actually have this Dinkin diagram for D4, that's SO8. It makes sense when n is 2. It's totally good when n is 2, but the Dinkin diagram is just 2 separate dots. In that case, this would be SO4. And SO4 is actually just the same as SL2, direct sum SL2. So that's a kind of degenerate case. SO4 is actually not a simple Lie algebra. I guess you can think about SO2, but that's just a trivial Lie algebra, so that would have no vertices in the Dinkin diagram. Let's go back to the general case again. Okay, so I'm back to our general Cartan decomposition. Let's now pick a base, delta, for the root system R. Hence you get this decomposition of R as a disjoint union of positive and negative roots. So I'm going to use all the standard notation we always use. The base is going to be alpha 1 through alpha L. L here is the rank. We showed at the end of chapter 2 that you could pick any non-zero E alpha in G alpha for each positive root. Any alpha, remember G alpha was one-dimensional. Just pick any non-zero vector E alpha in G alpha. And then there's a unique non-zero F alpha in G minus alpha. So the bracket of E alpha with F alpha is this special element called H alpha that we had before. H alpha, that was the element of T star which corresponded to alpha check under our identification. So remember, we defined it actually as twice T alpha over T alpha, but it's just the same as saying it's the element of T corresponding to the co-root alpha check in T star. And then also automatically H alpha E alpha is 2E alpha, and H alpha F alpha is minus 2F alpha, so that this subalgebra S alpha, the span of E alpha, H alpha, F alpha, was isomorphic to SL2 of C. So these were these SL2 triples which played a crucial role when we were proving those lemmas, constructing the root system in the first place, discovering these integrality axioms of root system. This produces, all these choices, produces a basis. So you need these E alphas and F alphas for all positive roots alpha. And then you use, actually I'm going to just denote them H1 up to HL. So HI here is going to just be a shorthand for H sub alpha I. So those are the H alphas corresponding to the simple roots, the roots in our base. And here I'm actually also going to adopt the same shorthand. I'm going to denote by EI, it's going to be E alpha I, and FI is going to be F alpha I for short. Okay, so this produces kind of a nice basis for the Lie algebra G, E alpha, F alpha, and these HIs. It's not quite canonical, right? There's choices involved. For each positive root, there's a choice of an E alpha. But apart from that's the only choice. So we might come back to those choices and refine them a little bit later on. Let's prove one last lemma today. So the lemma is that the Lie algebra G is generated as a Lie algebra just by the EI and the FI, the I in I. So just those simple E alphas and their negatives, the F alphas corresponding to those. Those are enough elements. There's 2L of them. L is the rank. 2L of them, and they generate the Lie algebra G as a Lie algebra. So what I'm going to do is I'm going to take a positive root, and I'm going to show that E beta lies in the Lie subalgebra of G generated by the EIs. Similarly, each F beta lies in the subalgebra generated by F1, FL, and then taking commutators. The commutator of EI with FI gives you HI. Hence you have a basis. Okay, so it's just enough to prove this first statement that I made to establish that in fact the simple E alphas and F alphas generate. So this goes by induction on the height of beta. Remember, the height of beta is a sum of simple roots. The height was how many simple roots you needed. If it's height 1, then it's beta is one of the alpha i's, and you have EI already. So there's nothing to do in the base case. And then if height of beta is bigger than 1, well, then you can use one of those lemmas in chapter 3. I think it was lemma 4. It tells you that you can find an I so that beta minus alpha I is a positive root. And then you have E beta minus alpha I by induction in this subalgebra. And it suffices to show that the Lie bracket of EI with E beta minus alpha I, remember EI is E alpha I, suffices to show that that's non-zero, then it's necessarily a non-zero multiple of E beta. But we already saw how to do this, actually. We saw that the SL2, S alpha I, the SL2 associated to alpha I, acts via the adjoint representation. We took the direct sum of all these beta plus R alpha I for all R in Z. And moreover, we saw that was this alpha I string through beta. That was an irreducible SL2 module. So it follows that any non-zero vector in this module, such as this vector, generates every other vector in that module by acting in this way. So in particular, if you act with EI, it must add alpha I onto it. You're kind of moving up that string. So we know that's non-zero because of this irreducibility of this thing as an SL2 module. Okay, so that's the proof. Let's finally introduce just a little bit more notation. Let's let n plus be the span of all the g alphas for positive roots, and n minus be the span of the g alphas for negative roots. So our Cartan decomposition actually gives us the following. G is actually n minus direct sum t direct sum n plus. And I'll usually denote this subspace, t direct sum n plus, I'll denote it by b. B here is for Borel. And let's note that n plus and n minus are both nilpotently algebras. You see, if you've only got positive roots, if you take two positive roots, g alpha and g beta, their bracket is g alpha plus beta, you never get to zero. You get higher positive roots when you do that. And so it follows easily. Well, all of this is a subalgebra, and all of its elements are ad nilpotent. So it's a nilpotent Lie algebra by Engel's theorem. Also, actually, this B is actually a semi-direct product of T. N plus is clearly an ideal. T normalizes n plus, so this is a semi-direct product, and since T is abelian, B, this Borel subalgebra, is solvable. In fact, it's a maximal solvable subalgebra, and that's the formal definition of Borel subalgebra. So these will all be useful. This decomposition that I've ended up with here, this is called the triangular decomposition. Of G. So it depends not only on the choice of a maximal toral subalgebra, which we needed to get the Cartan decomposition, but it also depends on the choice of the positive and the negative roots, i.e. the choice of the fundamental chamber, or equivalently the choice of the base of the root systems. To get this triangular decomposition, you kind of have to choose that order. You should think about this for the case of SLN. For that, we already worked out that the roots were these plus or minus epsilon I minus epsilon j's for I less than j less than or equal to n. This was the type A root system, and if you choose the positive roots just to be the strictly upper triangular, so to be the epsilon I minus epsilon j's for I less than j, then for that the G epsilon I minus epsilon j, that was the C span of the IJ matrix unit, and so with the standard choices, this n plus is exactly the strictly upper triangular matrices, and this n minus is exactly the strictly lower triangular matrices, and the Borel, it's the weakly upper triangular matrices. So that kind of hopefully explains the choice of the language triangular decomposition here. When you do it for SLN, it's just the usual decomposition into lower triangular diagonal, upper triangular matrices. And in fact, the SO2n example earlier, you again see the triangular decomposition reflects the decomposition of this matrix Lie algebra to upper and lower triangular ones. Same with the other classical Lie algebras, by the way. Okay, so it's all set up now. We've proved that G is generated by these simple EIs and FIs. The next thing is we've got to work out what relations hold between them. So we'll get to that in the next lecture. We're going to come to the kind of the final decisive result, which is the Serre presentation for G.